Okay, in this presentation we are going to look at a uniform random variable and its connection to the exponential distribution by means of a transformation. This is the transformation in particular. So let u be a uniform random variable on the interval 0 to 1. This is the sort of default setting of the uniform distribution, a continuous uniform distribution, and it sort of comes up quite a lot in computer science, Monte Carlo simulation, and random number generation, and so forth. Let x equal minus the log of 1 minus u, and what we're asked to show that x is an exponential random variable with rate parameter lambda equal to 1. Okay, so typically we would express the exponential random variable in terms of the rate parameter lambda. So there we have it there. So if a rate parameter has this distribution, we would write x is essentially an exponential random variable with a rate parameter lambda. The cumulative distribution function is given as follows. So where x is greater than or equal to 0, this will be the cumulative distribution function. Where lambda is equal to 1 and where x is greater than or equal to 0, essentially what we can say is that is equal to 1 minus e to the minus x. Okay, so that helps us out. Okay. Now, so the first thing we have to sort of establish is the range of the random variables, both in the context of u, which we know to be 0 to 1, but also let's look at x, the range of x, that would be 0 to infinity. What you do there, just to check that, and you should check that, is just let, in this expression here, let u equal to 0 and find what the possible value of x is, and then let u equal to 1 and again find what the possible value of x is. Okay? The upper limit there are get as close as you can. You should get 0 to infinity. So it's any positive real number or non-negative real number. So what we have to do is find the cumulative distribution function of x. Now this is a subtle but important point that I'm about to talk about here. Okay, so I'll just highlight it here. So if u is a uniform random variable, okay, that's important in this particular question on the interval 0 to 1, and k is a real number on that same interval, okay, between 0 and 1, then we can say that the probability of u less than or equal to k is equal to k automatically. Again, this applies specifically because we are dealing with a uniform random variable on the interval 0 to 1. Very specific to this context that we can apply this simplification. Okay? So where x, small x, is a real number on the interval from 0 to infinity, we can say the following. So capital F of x is the cumulative distribution function, and that is the probability of capital X being less than this real number, which is small x. So what we can do is substitute in the transformation of u, or our expression of the transformation of u that will give us x for that number. And that is minus log of 1 minus u less than or equal to x. So the probability of that, okay? Now what we can do here is apply some transformations and algebraic rearrangements. Now what you have to do there is just be careful about how this affects the sign, the direction essentially of this operator. So we have less than or equal to x here, okay? So if I want to exponentiate both sides, I can just do so. The exponential of minus log of 1 minus u is essentially 1 over 1 minus u, and the exponential of x is simply the exponential of x. Okay, so essentially I can go from here to here just by exponentiating both sides of that operator. What I'm going to do now is invert both sides, okay, and something I just sort of spotted there is that I should have actually had the change the direction of the operator. Okay, so I'm going to invert both sides. So I have 1 minus u greater than or equal to e to the minus x. Okay, now what I'm going to do there, so that's an inversion, and what I'm going to do now is get the complement of both sides. And what happens is that the operator goes back to the way it was before, less than or equal to. So here, inversion, we switch the direction of the relational operator, and when we use the complement again, we switch the direction of the relational operator. Okay, so that's just a sort of, you'd be very careful about stuff like that. So then we have, when we get the complements of 1 minus u, that's simply u, and the complement of e to the minus x, that's simply 1 minus e to the minus x. we have this expression here, the probability of u less than or equal to 1 minus e to the minus x. Okay. Something you should do actually is just check the range of possible values of e to the minus x, and essentially it should be some number between 0 and 1. Okay, so just check that so you just make sure you're satisfied with it. Likewise, 1 minus e to the minus x, that should be also a number between 0 and 1. Okay, now that is where we invoke this formula here above. K is a real number on the interval 0 to 1, okay, and that's a real number on the interval 0 to 1. So here we can invoke this expression here. So we can go simply restate it as follows: probability of x less than or equal to x is 1 minus e to the minus x. Okay, that's the cumulative distribution function. Okay, so that's the cumulative distribution function of the exponential random variable rate parameter lambda equal to 1, and that demonstrates what we need to do. So what the hard things there, essentially, again, the relational operators, which I dropped the ball on myself when I was writing this up, but also this thing here, which is very easy, straightforward, but you need the presence of mind to remember it when you're, doing this question here, okay? Because you just get stuck here at this point, not realizing you can automatically go to that point just by invoking the above concept. Okay, great. Leave it there.